Sit down, buddy. Can't have you touching everything.
All right. So what we're going to do today is we're going to start what we'll call Chapter 6. And Chapter 6 is all about radical functions. When I say radical functions, I'm not talking about surfer functions that are like totally radical, dude. Instead, what we're talking about are things that involve like square roots or similar things.
Is this chapter similar at all to last chapter?
Nope.
Beautiful. Let's see. All right. Yes, sir.
Yes,
Yes, sir. Come on, man. Love to see it. This is like calculus. This looks like calculus, man. Yeah, that's what's up.
So a radical function is just something that can be written in the form a times the nth root of x minus h plus k. So we're probably not too familiar with the nth root symbol, but the nth root is just a category of operations, one of which is the square root. So one type of nth root is a square root. And we're familiar with square roots, and that's kind of where we'll start in this chapter, is kind of talking about square roots. So let's just kind of take a moment and kind of familiarize ourselves a little bit with this notation and kind of what it's really saying. So when n equals 2, what we're talking about is a square root. And what do we mean by a square root? Well, what we mean is if the square root of a is equal to b, that tells us that b squared is equal to a. Right? This is the basic definition that we've been using. Like, for example, the square root of 4 is 2 because 2 squared is 4. Right? Is everybody okay with that idea? Now, this value for n that we've tucked in here, this is called the index. I guess I should mention that, as I'll end up saying it at some point, and you guys will look at me like, what the heck is an index? It's just that number inside the check mark part of our radical. And you notice on a square root that we don't bother to write the 2 there, right? Now, we do this kind of thing all the time in math, right? We don't bother to write the 1 in front of a variable, right? We don't bother to write 1x, we just say x. We don't bother to put the 1 in an exponent. We don't say 2 to the first, we just say 2. The same kind of thing here. We don't bother to put the index of 2 in with our square root. We just write the symbol and understand that if there's nothing there, we're talking about a square root. Everybody's okay with that idea? Now, another one that we've talked about just ever so briefly when we talked about some of these factoring things is a cube root. So what we mean by that is if the cube root of a is equal to b, that means b to the third is equal to a. And the place we had kind of seen that before is in previous chapters when we were trying to factor sum and differences of cubes. We're often interested in determining if, like, is 8 a perfect cube? Well, we knew it was because 2 times 2 times 2 is 8. You guys kind of remember doing that from a couple chapters ago? We still kind of did it even in the last chapter, right? I think there's a cube that popped up here or there in the homework. Ben? Sure. So we can kind of keep doing this. So in general, for any integer n that's greater than 1, we can say then that the nth root of a is equal to b if b to the n is equal to a. So just, and the same kind of definitional pattern continues for any values of n. Let's say any whole number values of n that are at least 2. Right, that's basically what we're saying. So it works the same way for 4th roots and 5th roots and 6th roots and 7th roots and 8th roots and 9th roots and 10th roots and on and on and on and on and on. So before we can move on and start talking about these radical functions in particular, I want to spend a little bit of time just talking about how we deal with radicals in general, like so square roots and cube roots, how we kind of reduce these things and simplify these things and multiply them together and add and subtract them and do all this kind of normal basic 4-function operations. Okay? So first thing we'll do is talk about reducing radicals. So I'm going to just kind of do a bunch of examples here. I'm not going to give any like descriptive notes because I think it's just easier to kind of see what's going on with numeric examples rather than doing this abstractly. So let's say that we have the square root of 8. Now you should be able to look at the square root of 8 and go, well, 8's not a perfect square, right? I know that this 2 squared is 4, and I know 3 squared is 9. 8 falls between 4 and 9, so there's not a whole number squared that gives me 8. Everybody okay with that? That should feel reasonably okay. However, maybe there's a factor of a perfect square inside of 8. So for example, 8 is 4 times 2. Everybody agree with that? Why is that advantageous? Well, it's advantageous because 4 is a perfect square. So one of the features that we have for these radicals is that you can kind of break a radical at a multiplication symbol. So the square root of 4 times 2 can turn into the square root of 4 times the square root of 2. And the square root of 4 is just 2. And the square root of 2 just stays the same. And this would be our reduced radical. So you notice the number inside the radical has gotten smaller, but we've picked up a coefficient outside the radical. That's the usual process. Is every radical reducible? No, right? Square root of 2 doesn't reduce anymore because there's no perfect squares that are a factor of 2. But some of them can. Let's do a couple more to kind of make sure we get the handle on this. Sound okay to you guys? Oh, good. How about the square root of 72? Is that 72 a perfect square? No, right? I know that 8 squared is 64 and 9 squared is 81. That lands in between them, so. Does anybody see a factor of 72 that's a perfect square? What's up? Okay, 8 and 9. 9 is a perfect square, right? Because 9 is 3 squared. So we can call this the same thing as 9 times 8. And then we could break it up, just like we did before. And the square root of 9 is 3. And the square root of 8. But is the square root of 8, is that as reduced as it can get? No. And in fact, we know what the square root of 8 is, right? Because we just did it in the previous problem. The square root of 8 is 2 square root 2. So then we have 3 times 2 square root 2, or 6 square root 2. Keep in mind, you can multiply stuff outside radicals together, and you can multiply stuff inside radicals together, but you can't take something from the outside and multiply it to something on the inside. Everybody's okay with that idea? Worth noting that a little bit quicker would have been had you done 36 and 2, since the square root of 36 is just 6. But what Megan suggested worked just fine, right? Took an extra step or two, no big deal. The point is getting to the right answer. We didn't have to get out a calculator and do anything. We just used mental math, and we found a times table number that had a perfect square in it. Got a little bit simpler. After it got simpler, it was much easier to find any more perfect squares. That's one of the advantages of this. Doing this is that every time you simplify or you do a little bit of reducing, if you didn't get all of the reducing, it's going to be easier to find the next step, right? Because the numbers have just gotten smaller. Everybody okay with that? Let's do another. About 126. This is decidedly not a times table number, right? Probably most of us look at this and go, well, I don't know what anything that divides 126 right off the bat. Certainly I don't know any perfect squares that go in there. So if you're stumped, this is kind of the best way to go, is to just look at a prime factorization. So 26, what's any number that we know is going to divide 26? How about 2? Why do I know 2 is going to divide it? Because it's even, right? If I divide this by 2, I get 63. Now 63 I recognize as a times table number, right? What is 63?
It's 9 times 6.
7.
7. Yeah.
And then 9 is 3 times 3. So 126 is 2 times 3 times 3 times 7. But specifically what I'm interested in is the 3 times 3 part. Why am I especially interested in that? Because that's a perfect square. So 3 times 3 is 9. So I can break this up then as the square root of 9, square root of 2, and the square root of 7. Or 3 square root 2 times square root 7. And now notice square root 2 and square root 7 we can't do anything more with, right? So typically what we do is we squish those back together and make a square root 14. And again, it's okay to multiply those together because they are both under a radical. So you can multiply the stuff under the square roots together, and you can multiply the stuff outside the square roots together, but you can't multiply inside to outside. Does this feel okay?
Yes.
Not a big deal, right? In fact, this feels kind of a relief because it's very numeric and it's not abstract and it's not symbolic. It should be relatively straightforward. What if instead we had the cube root of 54? This time, instead of looking for perfect squares, I need to be looking for perfect cubes. What are some examples of perfect cubes? 8 is an example because 2 to the third is 8. What's another one? Well, let's do what's
64.
3. Okay, 64 because 4 to the third is 64. What's in between 2 to the third and 4 to the third?
3 to the third.
Okay, what's 3 times 3 times 3?
12.
27.
27.
27.
So, let's check 54. Does 8 go into 54?
Yeah.
No.
No.
No, it goes to 56.
It goes into 56, but not 54.
Yeah.
Does 27 go into 54?
Yes.
Yes, right?
Four is good.
Yes. So 27 times 2 is the same thing as 54. And then I can break it up. The cube root of 27 is 3. And there we go.
So does that, like, power to the 9, that number changes, really? The little 3 in between the...
Right, the index doesn't change
Okay.
on these reducing problems. That is correct. Howdy, sir. What's up with you? Okay. Let's do cube root negative 432. Now 432's, well, a big number, but before we even deal with that part, what do you notice that's different about this problem than any of the previous ones we've seen to this point?
You got a negative.
It's negative. Now, we know if we tried to square root a negative number, that's no bueno, right?
C.
That's no good in Spanish, for those of you that are unfamiliar. But is the same thing true for cube roots? Well, let's think about it. Are there any perfect cubes that are negative? What if I take negative 1 and put it to the third power? That's negative 1 times negative 1 times negative 1, right? What is negative 1 times negative 1 times negative 1? It's negative 1. So perfect cubes can be negative, right? We've just shown what there's one. So can we take cube roots of negatives? Yeah. And in fact, it extends to where we can do the cube root indexed radical, but we can't take the root of any the root of a negative for any even indexed radical. So square roots, fourth roots, sixth roots, eighth roots can't do negatives. Cube roots, fifth roots, seventh roots, etc. can do negatives. Is that okay?
So basically, like where your negative 1 is, it has to be an odd number there. You can't have an even number.
The index has to be odd.
Oh,
Yes.
oh, the index has to, okay.
Yes.
Okay.
Index has to be odd. The number underneath the radical can be odd or even. That part doesn't matter.
Just the index.
The index is what we care about. Okay with that, everybody? Now 432. Probably you look at that and I don't know what goes into, if there's any. So if you're not factorization, so what number do we know goes into 432? 2. Because it's even, right? Is there other stuff? Sure, but I don't want to try that hard to find it. I'm just going to start with the obvious one that I know. And plus, dividing by 2 is really easy. How about 216?
Yeah, you can do that again.
Yeah, let's 2 that again. That gives us 108. How about 108?
2.
Do the 2 again. Damn it!
Hold up. What happened?
54, that number looks familiar. We know what the cube root of 54 is. We already did that problem before. So I'm going to stop my prime factorization here and just borrow the work that I've done in the previous problem to finish this thing up. Is that okay? If you didn't notice that, it's fine. You could continue going. But you're going to find when doing these assignments that oftentimes you're going to find recycled work inside of these problems that you're welcome to take advantage of. So what I'm going to say here is 432 is the same thing as 2. Is that okay?
Never restarted, so that's why you left the Zoom.
What? Oh, Jesus. I'm so frustrated by all this nonsense. Whatever.
Seriously thinking about investing in photos. I think I'm gonna go after school, go get some photos. 100%. If it doesn't work, then I might have to just cut my nose off. Dude, I've been taking everything for my shots, but it's not working.
So good. Take one for the physical pain, one for the emotional pain, and you're all set.
That was good.
George, you want to focus?
No, dude, I have student events. I'm straight.
Okay.
Thank you, I appreciate that.
So, the cube root of -1 was -1. The cube root of 8 is 2. And from our previous problem, the cube root of 54 is 3 times cube root 2. When I multiply the stuff outside the radical together, I get -6. And then I have the radical part, cube root 2.
It wasn't that bad.
Not that bad, right?
I mean, it's still bad, but it's not that bad. No.
Well, what's nice about it is that it's all numeric, right?
Yeah.
There's no variable. It's not abstract. It's just like rearranging some numbers. What's up, Mark? Yep. All right. So what are we going to do if we, say, want to multiply? So let's say we wanted to multiply the square root of 6 and the square root of 75 and write our answer as a reduced radical. Well, one way we could do this is we could start by looking for perfect squares in either radical. Are there any perfect squares inside of 6? No, because 6 is 2 times 3, right? Neither of those is a perfect square. How about 75? 25 times 3 is 75, and 25 is a perfect square, right? That's 5 squared. So let's do that. Everybody's okay with that? Now the square root of 25 we said was 5. And then I can just smooth that we can't do anything with, because the square root of 6 and the square root of 3, neither one of those contain a perfect square factor. So we can just multiply those parts together and make the square root 18, right? Yes, sir. We'll talk about why that might be a good or bad idea, depending on the situation, in just a second. What do you notice about the square root of 18, though?
It's not a perfect square.
But does it have a factor that's a perfect square?
9.
9. Yeah, so after you multiply, we still have to make sure we go back and check. Except it's 2, not 3. Now, Woody had suggested, well, couldn't we have multiplied from the beginning? Sure, that's acceptable. Let's go see what that would have looked like. So 6 times 75 is 300, right? Is that right? No. 450. Okay. And now we can either, if we notice any perfect squares, we can use that, or we can go through the prime factorization. Does anybody notice a perfect square here? 25, okay. And the other part of it is 18, I believe. And if we wanted to even, we could say, oh, 18 is 9 times 2, right? Might as well do it now. You know what I mean? Yeah. So 5 times 3 times root 2, or 15. Still ending up at the same place. Is that okay with you guys? Okay. So what's the advantage or disadvantage of doing the multiplication first?
Well, it's a bigger number, so maybe you can make more mistakes.
Okay. I think the bigger number just means it's going to be harder to break it apart, right?
Yeah.
Because it's going to be more difficult to see the perfect squares inside. It'd be take a little bit more time to do the prime factorization. The advantage, though, is it's potentially less steps, right? If you do see the perfect square, it's going to be, if you notice that, like, better than 215, if you notice that 225 is a perfect square, you could have done that in really just like one step. Because 225, I don't know if you know that or not, is just the square root of 15.
So you could have done that probably in one step right there.
Yeah, if you would have done this, would have been the minimum work. But that you to know that 225 was a perfect square, which maybe you do, maybe you don't, probably not. I don't know that anybody has any experience worrying about squares past 12 that are the times table numbers, but you might have. But yeah, so if you do the multiplication first, you have the advantage of, if you see it, it's fast. If you don't, you've potentially made a bigger mess than your bigger mess. Let's do another, yeah?
Yes.
Okay. Oh boy, what just happened? Oops, this needs a letter.
Mr. Cool, can I go to the bathroom real quick?
Absolutely.
Appreciate that.
No problem, G. Don't take his tissues.
We should take all the tissues out of the box and get back to
and put all the tissues in his backpack. Where are my tissues? Look close to the back.
So, here's an example of a situation where you probably don't want to multiply everything together, because 30 times 105 times 224 is going to be a pretty stinking big number. And it's going to kind of make maybe a bigger mess out of this than you really need it to be. Is that okay? You guys can see the reasoning there?
Yeah.
So what we'll do instead is we're just going to do prime factorizations. So 30 is 2 and 15, and 15 is 3 and 5. 105 is 5 and 21, which is 3 and 7. 224 is 2 and 112, which is 2 and 56, which is 2 and 28, which is 2 and 14, which is 2 and 7. So let's shortcut up our work here a little bit since we've gone and done this prime factorization. So I have 2 times 2, that's a 4. I have 2 and 2, that's another 4. And I have 2 and 2, that's another 4. Everybody okay with that? Okay. And then let's see, I have a 3 and 3. That'll give me a 9. And then I have a 5 and 5. That'll give me a 25. And then lastly, I have a 7 and a 7. That'll give me a 49. And I have all perfect squares here, right? So when I break this up, I'm going to have no square roots left over, which is pretty cool. So I have 2 times 2 times 2 times 3 times 5 times 7. Which is 840. When I type that into my calculator. Is everybody okay with how I took that prime factorization, kind of shortcutted to there? By just anything in the prime factorization I can kind of pair up to make perfect squares. Now, does this problem change if we're doing cube roots? Probably. Let's say these are our cube roots. Again, probably not a problem where I'd want to multiply everything together because you're just going to get a monster number out of that. That'll be a pain to try to simplify. So instead, what I'm going to do is just go and do the prime factorization. So 81 is 9 and 9. So that's, each of those is 3 and 3. 128 is 2 and 64. and that's 2 and 32, and that's 2 and 16, and that's 8 and 2, and 8 is 2 and 4, and 4 is 2 and 2. I guess I could have stopped here at the 64. That was a perfect square. I don't know why I wouldn't have done that. Because we're not looking for squares, we're looking for cubes.
So if you do the perfect square, like if you go from
Here,
64
this will be easier. What if I just did 64 is 8 and 8, because those are cubes. That's the better, right? Let's do that. That saves some space. But yeah, if you're doing the prime factorizations, if you go hunting and you find like perfect squares or perfect cubes in there, you don't need to go past there depending on whether you're using a square root or a cube root in the problem. So 750, let's just do 10 and 75. That's probably the obvious way to go. So that's 2 and 5, and that's 3 and 25, and 25 is 5 and 5. And now let's collect what we've got. So looking at our threes, 1, 2, 3 threes. That'll get me a 27. And then I have 1, 2 more threes. That doesn't help any. I'll just put that as a 9 there. And then let's look at, we have 2 8s. So 8 and 8. And then we have just 2 2s. That doesn't help us any. I'll just put a 4 in there. I'm going to underline those guys though, acknowledging that I don't have perfect cubes there. Actually, let's just let's do this. Actually, let's do a different color scheme here. Three times 3 times 3. See the 3 yellow threes?
Oh, I was looking at the four.
Okay. And then we'll do, I have 3 5s. 5 times 5 times 5 is 125. That's a perfect cube. And then I have these leftovers. Right? None of those have 3 apiece. I have 2 3s and 2 2s, so I can't make any more cubes out of those. So I'm just going to stick all that stuff together. 3 times 3 times 2 times 2 is just 36. Everybody okay there? Or no? I'm just trying to shortcut up through some of this stuff. Hallie, what's up? I do. But 8 is a perfect cube.
Oh, okay.
Was already a perfect cube. That's why I stopped at something that wasn't a prime, is because it was a perfect cube already.
Okay.
So I have cube root 27, cube root 125, cube root 8, cube root another 8, and then cube root 36. So cube root 27 is 3, cube root 125 is 5, cube root 8 is 2, and cube root 36 we can't do anything with. 3 times 5 times 2 times 2 is 60. And that's as good as we can do.
Mr. Blue,
Yes, sir.
I have 2 questions.
Sure.
First one is, so when you got your 3 times 5 times 2 times 2, basically, are you saying that so like the 27, 3 to the 3rd power is 27, so that's why we're using 3.
Yes.
5 to the 3rd power is 125, and then
Yes.
obviously 2 to the 3rd is equal to 2. So that's where we're getting those coefficients from.
Yes.
And then since 36, that's the end number, right? That's 36.
Yep, that's a 36.
Since we can't find There's nothing that like to the power of 3 equals 36. We just leave it as it is.
Right, because 36 was 2 squared and 3 squared.
Okay.
So there's no powers of 3 in there.
Okay.
So it just stays 36.
All right. And then what happened to the 2 times 2 with 4? Do we just not use that, or do we put that in somewhere else?
The 2 times 2, where do you see?
The purple.
The purple is the 36.
Oh. So
2 times 2 times 3 is 36.
So did you just multiply the leftover numbers you had?
Yep.
Okay.
Anything that I couldn't put into a group of 3, just all pooled together into one.
So basically, we can only do a group of 3. Like the first one obviously has to the left of the 81, we have 4 3s, but we only need to group 3 of them. So that's
Well, I highlighted the 3 yellow ones
Yep.
that I used.
Looks good. Okay.
Yep, but that's exactly what I'm doing, Joe.
Yeah. Okay. That makes more sense. Thank you.
Yep. What do you guys think? You think you're ready to try some on your own?
Yeah.
Okay. So in the content library, you're going to see homework 1 for chapter 6. Notice it says 2 pages on it. So I put the 2 pages horizontally rather than vertically, so maybe it would be easier to see that. I think last chapter I had a 2-pager that was vertical, and seemed like half the class missed the second page of it because they just didn't keep scrolling or whatever. So I put this one on horizontally. But the first 10 questions are just reducing. And the last 10 questions are multiplying. So many of them should be pretty easy, but they'll get a little bit progressively more complicated as they go. But by and large, they should be pretty doable. The factors are all small. I didn't do any I don't think I even have any double-digit primes in there anywhere. So just like 2s and 3s and 5s and 7s and stuff. I don't think I have like a 17 or anything. I've stuck in anywhere to make it just a pain in the butt to factor it. So they should be pretty doable. So you guys